something related with stellar physics, and in particular nuclear reactions that occur in stellar interior, and their impact on observable that can be usable, so astronomical observable, like luminosity, temperature, evolutionary time scales, something that can be measured with stellar photometry or spectroscopy, and that can be used to constrain the physics, and in particularly to check if new physics is needed in order to explain what we observe. Okay, of course, this is a multidisciplinary discipline, and so I have I collaborate with a long list of people here. There are some of them the most closer to me. Not working? Okay, now yes. Okay, so the problem is of the need of new physics is well known. Now the fundamental theory, quantum field theory, have provided before the 1980 the theoretical framework of the so-called standard model that explain what is observed in laboratory experiments concerning particle, the constituent of matters and the carrier of the fundamental interactions. By the way, these models, these so-called standard models, have some issues, some drawbacks. For example, one of the most famous is the so-called CP problems, that is the conservations of the CP by the strong interaction in contrast with what the theory predicts. No, the theory allow a violation of the CP in the QCD sector, but actually no experiment have found processes in which this violation really occurs. And this is something related also with the measurements of the electric dipole moments of the neutrons, that actually experiments tell us that should be very small, much smaller, 10 order of magnitude smaller than expected in the framework of the standard models. And then there is a more general problem is that everybody know, that is the necessity to understand the nature of the dark matter, no? And all these are strong motivation to investigate new physics. And among the various proposed theoretical development beyond the standard models, there is the proposal of these particle actions that may provide some solution to these very low-standing problems. Sorry. So here the motivations in the theoretical, in the theory, in cosmology, and in astrophysics to consider actions, these particles, or Alps action-like particles. In particular, in cosmology, I have already recalled the question of the search for the dark matter candidates. And in the theory, there are these problems. And in astrophysics, there are these two very interesting problems. One is the transparency to photons of the universe, which appear to be much more transparent than expected in the base of the opacity of the intergalactic mediums. And actions can provide an explanation of these transparencies, of this reduced opacity. And the other problem that is the ones I will concentrate in the next part of my talk concern the anomalous cooling in stars, in case actions are small enough to be produced by thermal process inside the stars, like it happens for neutrinos. Okay, so this is just to remember you the question of the charge parity violations that is allowed in the standard model, in the part of the Lagrangian, of the QCD Lagrangian, and actually experiment show that this is not the case, and this is related with the existence of a known vanishing electric dipole for neutrons that actually also in this case the experiment showed that it is actually at least 10 order of magnitude lower than expected. And so why action? Action was introduced in 1977 by Pechet and Quinn as a new symmetry actually, that this symmetry was spontaneously broken in the early universe, according to this theory, and thus the Nambu-Goldens boson that is released after the symmetry breaking was called actions, and the mass of the actions is inversely proportional to this factor F, that is the energy scale at which the symmetry was broken, and also the strength of the interactions, that is what we want to constrain, the strength of the interaction with standard model particles, so with photons, action to photons interaction or action to electrons interactions, also this strength scale inversely with the energy. So the symmetry was broken. The symmetry was broken. This is the story of the universe from the Big Bang to nowadays. So the symmetry breaking occurred, and the smaller is the mass and of the actions, and the weaker is in the interaction with standard model particles. And so according to for cosmology, in order to be good dark matter candidates, the symmetry breaking should occur before the electroweak symmetry breaking, so very early in the universe, at an energy of the order of 10 to 3 JeV, okay, at this energy scale. And in that case, the mass of the actions is of less than milli electron volts, and in that case, the small mass prevents decay into other particles, so they are long-lived particles in this case, and so for this reason they may behave as cold matter. And another interesting feature in cosmology is that the presence of actions may affect the expansion rates in the first 3 minutes before the Big Bang occurs, the Big Bang nucleosynthesis occurs, sorry. And in that case, the expansion rates affect the product of the Big Bang nucleosynthesis. As you know, in particular helium, no? The faster is the expansion, and more neutrons are conserved at the times of the Big Bang nucleosynthesis occurred. And so more neutrons means more helium produced, no? Because most of the neutrons goes into helium. And so also the deuterium is affected, the deuterium abundance is affected. So by comparing, so essentially this is the Friedman-Lemaitre equations that in a standard cosmology, you know, an homogeneous and isotropic universe give us the expansion rates, the R dot, that is R is the scale factor, the length scale factor of the universe, and this depends on the density, total density, and the curvature. This term is negligible in the early universe because the energy density is very high, and these are the component, the most important component, dark matter, dark energy. It doesn't matter in the early universe. The early universe is radiation dominated. So essentially photons, because of this power law with the temperature. And so at a very high temperature, this quantity dominates. And in the standard model, we have photons, electron positons, and neutrinos and antineutrinos. That's all. So we have to sum this density, and this is the results here. one known results. And in the standard models, this NF is 3, no? Actually, a little bit more because there is a small contribution when the electron and positron annihilates. There is a weak channel. Now, most goes into 2 photons, but there is a weak channel that produces neutrinos and antineutrinos, and it is usually accounted with this little bit more than 3 neutrino types. But if there are other relativistic or partially relativistic particles, they may give a contribution to the energy density, and then it's modify the solutions of the Friedmann-Lemaitre equations. And so in non-standard models, there is the possibility that NF is larger than 3, and this can be measured comparing the results of the BBN calculations with the observed helium and deuterium abundances. And this is currently done by people that work on that. So of course, in order to do this job, the nuclear reaction involved in the BBN should be known with very high precisions. And this is a work that is ongoing still. And also the measurements of the abundances, but this is a matter for astronomers, should be improved in order to have a better understanding of this important parameter NF. Okay, so this is just to show you a very old slide. This that out changing the number of neutrino spaces, the yield of helium increase. Okay, because you have more neutrons, and so if the NF is larger, the density is larger, the expansion rate is larger, so you have more neutrons and a larger amount of helium. Okay. So let me go to star now. As I told you, if the mass is small enough, they can be produced in the core of the stars, and then by thermal process, like this one here. So the Primakov one, photons in an electromagnetic field, so virtual photons that have this vertex field that can produce action. This is the so-called Primakov. Then there is the Kopfman scattering, the T plus is minus annihilation, which is important for massive to very massive stars. And Bremsstrahlung in the generate core of stars, right? Red giant, asymptotic giants, or near the end of the massive star lives, this Bremsstrahlung may becomes an interesting possibility to produce actions. Okay, so the mass should be small because the thermal energy should be enough to produce these particles. Okay. So how they modify the stellar evolution, let's say. Okay, this is the well-known energy conservation equations in which we have the luminosity gradients here, and here all the processes that produce or absorb energy, consume energy inside a star. So nuclear energy rates, gravitational energy rates, contraction and expansion. And here we have the neutrinos, okay? And that's so we may integrate this one and get the luminosity that can be compared with what we observe, the luminosity of stars. So very simple in principle, nothing particularly difficult to do. Okay, so suppose that you find a discrepancy between what you predict and what you observe. How you can interpret that? Well, the first interpretation may be that there are some input physics. For instance, nuclear reaction rates are overestimated or underestimated. Okay, so this produce this is at the origin of the discrepancy we found. But the other possibility, if you are sure, if you can reduce these uncertainties, observe in the observations, in the observed luminosity, for instance, and in the theoretical recipes. So thermodynamics inside the star is well calculated. So the nuclear reaction rates are well calculated. The neutrino rates are well calculated within a small error. And so what remains is the possibility that we are missing some physical ingredients, and that's what we want to do. So some example of missing physics and no vanishing neutrino magnetic moments. Now in the standard models, the magnetic moment of neutrino is very small. It depends on the mass of neutrino, and since the mass of the electron neutrino is extremely small, the magnetic moment is small, and have as a matter of fact, have a negligible consequence of the neutrino production rates. But in theory beyond the standard models, the dependence of the neutrino dipole moments and the mass is much steeper, and in that case we may have a modification of an increase of the neutrino rates, because you have an additional interaction, an electromagnetic interaction in addition to the weak interactions, and this increases the possibility to produce neutrinos. Okay, so and the other possibility, the other example is the possibility to produce by thermal process non-standard particles, and this is the case of actions. And in case the mass is of comparable to the thermal energy that we have inside the star, I don't know, of the order of 100 of keV. In that case, the particle is produced near the center, and then move outward, and then can decay into the stars. In that case, we have an energy transport inside the stars, an additional mechanism to transport energy from the center to outside. And if the mean free path of this particle is small enough, we may use a diffusive approximations like we do commonly for photons. And in that case, we have to modify the opacity. If the mean free passage of the order of the stellar radii, in that case, it's a little bit more complicated. We need the ballistic models, sort of ballistic models, to treat this kind of particles, but it can be done in any case. Okay, so let me show you some results we can get with these techniques, with these methods. And let me concentrate on globular cluster. I suppose that many of you know globular clusters that populate the halo of our galaxy, but they are common building blocks of any kind of galaxy. We found everywhere globular clusters. Globular clusters are clump of stars of 10 to 6, 10 to 7 stars, so a very large number of objects, and this is the reason for which they are interesting objects to study this deviation from the standard physics. Okay, so of course, in the last 10, 20 years, there was many improvement in our observations of globular clusters in photometry and spectroscopy and astronomy. Astrometry, sorry, it's very important because allow us to distinguish between stars. Now we measure relative velocity, radial velocity or angular velocity of stars, so the motion of the stars, and then we can also measure parallaxes with astrometry, so the distance of these stars, and this is very important. So we have now this satellite Gaia that provides us very precise measurements for stars, for billions of stars in our galaxy, and including most in the halo. And so this is the kind of improvement that we have. So globular cluster and actions. So from where we can get information about actions, looking, for instance, at the luminosity of the tip of the Reggian branch. This is affected by Bragg-Strahlung action. So also the RGB luminosity function is affected by Bragg-Strahlung. The ZAB luminosity, the zero-age horizontal branch, so the stars that are starting the quiescent helium burning phase are affected by what happened before. So once again, Bragg-Strahlung actions. The Hell parameter, that is the number of stars observed in the horizontal branch in the helium burning pump, and the number of stars in the brighter part of the Reggian branch, or this number that can be measured is affected by action produced by Compton, Primakov, and Bragg-Strahlung. So also the RRI or mass RRI are pulsating stars in the horizontal branch. And in general, the pulsational probabilities are affected by Brestranums. And also the R2 parameters, that is the number of AGB stars over the number of HB stars, are affected by constant Primakov and Brestranum once again. So I will talk about these two. Okay, the luminosity of the RGB tip and the Hertz parameters. Okay, so the basic ingredients are essentially evolutionary tracks of stars with the mass of evolved stars in globular cluster, which is of the order of in between 0.8 and 0.9, according to the age, that is 12 to 14 gigayears. Okay, so obtained by assuming different strength of the interactions between action and electrons, so Brestranum and Compton rates, and the action and photons, so the Primakov and rates. So these strengths are normally indicated by these two parameters, G13 and G10. And this is what we want to constrain. They are known that what we want to constrain. Okay, so this is the theoretical recipes we have developed. If you are interested in how this comes from, the various rates that at the end are summed to get the rates, the energy that is lost per second and per gram of matter, essentially by the various process. Okay, if you are interested in theoretical development, you may search in the appendix on this paper in 2019, as in an EPJ Astrophysical Journal paper. So this is the helium flash, no? The stars at the tip of the RGB emit helium in the degenerate core, no? The electron degeneracy produce this kind of temperature profile, no? The energy redistributions within the core is very efficient because the degenerate electrons transport this energy, so there are conduction by the degenerate electrons, so they tend to become isothermal, the cores. But near the center, where the density is larger, plasma neutrinos cool down the core. So the temperatures move out. The maximum temperature move outside around 0.2, 0.3 solar masses from the center, and so the helium will emit here. And this is the first flash that you see. It can reach almost 10 to 10 solar luminosity, and then we have a series of smaller helium flashes that are obtained when the temperature increases in this region and the degeneracy is removed, until the star reaches the horizontal branch, the zero-age horizontal branch, the ZAB, and aqueous helium burning finally start. So here is the tip of the giant branch, and here is the zero-age horizontal branch. It starts the lower envelope of the horizontal branch here. So the luminosity of the bright star here tell us something about the physical mechanism, neutrino cooling, the degeneracy of the electron, and so on, that occurs during the giant branch phase. Okay. So, and you see here, this is the energy loss rates by neutrinos, the dashed line, that follow essentially the density profile. It's higher in the center because the density is higher. Instead, the actions profile of the epsilon, due to the action, it maximizes where the temperature is maximum. Because if you remember these slides here, all the various rates essentially depends on the temperature. For instance, depends on the temperature, the night power of the temperature, and on these coupling parameters. So, sorry. Okay, so we have this behavior. So we have neutrinos here, plasma neutrinos, essentially, and Brestranum actions. The other process, Compton, Primakov, are suppressed because of the degeneracy of the electron, but Brestranum survive and can produce action through this process. Okay, this is the effect. This additional cooling, additional to the neutrinos, provided by productions, make the condition for the helium flash are attained later. So there is a delay, and so it occurs when the core mass is larger and the luminosity of the star is larger. So increasing the coupling of action to electrons, that is the parameter that influence the action rates, we have that the bolometric magnitude, the luminosity, increase. Okay, so measuring the luminosity, we may constrain this parameter. That's the idea. Okay, and this is what we get with 21 cluster. As I briefly told you, we have used the improved distancing from Gaia, improved photometries with the HST and other that allow us to resolve the core, the crowded core of the globular clusters. And most red giants are in the core because they are more massive. So they segregate the dynamics. Now the globular clusters are collisional stellar systems, and since they are very old, there is enough times to redistribute the stellar mass, the stellar content is in agreement with their mass. And so the more massive object, the most evolved one, tends to be concentrated toward the center, while the other stars, the lighter star, the main single stars, are more distributed on a larger length scale. And so this is what we get, the luminosity of the RGB tip. The dotted line, red dotted line, is the least square feet. And these continuous lines is what we get without actions, okay? And this dotted line here, dashed line here, is when the coupling, sorry, this is wrong, this is 13, not 10. Okay, this is the coupling between action and electrons. And when this is 4, 10 to minus 13, these parameters, and we have this kind of RGBT, so brighter RGBT. So we have performed a statistical analysis. These are the likelihood. This is what we got in 2020 before the data registry of Gaia, and this is after. This is just to illustrate the advantage to have the recent Gaia measurements, and we got this very stringent constraint. Within a 95% of confidence level, we may say that the coupling of action with electron should be less than 0.96 10 to minus 13, and this is the most stringent constraint for these parameters. The experimental constraint, the laboratory experiments are 20 times larger than this one. Okay.
So when you say that it's smaller than 0.96, it could be 0. 0 would be
could be 0. But
be consistent.
Yeah, as I told you at the beginning. Sorry, the microphone. As I told you at the beginning, the mass and the strength of the interactions depends on the energy scales of the symmetry breaking. So the earlier, so the higher is the energy scales and the smaller in the interaction. So this is good because this confirmed that they could be very good candidates for dark matter. But at the end, I have a slide that shows you why this is important for the experimentalist. Okay, I will show you. But you are right, maybe it's 0, but maybe also very small. Okay, so they are whispers. They are called also whispers of ghost particles because it's very difficult to detect them. Yeah. Yeah, but 0, it's an extremely lower limits. It's like infinity. It's 1 over infinity. So but it may be 1 over whatever you want, but finite one. Okay, so we don't know. Okay, this is the progress we have made in the course of the years and with our latest results. But what I want to remarks is are we sure that we are the standard physics is under control? That's the problem. So in particular, this reaction, the triple alpha reaction, of course, play a fundamental role. No, the larger is the rates and of the triple alpha, and this may anticipate the helium flash, and so the helium flash may occur at lower luminosity. On contrast, a lower rates, low rates may produce brighter, so may, in some sense, simulate what action do. So we have to constrain these triple alpha reactions in a very small range of uncertainty. Okay, as you know, for temperature below, for temperature between, let's say, 100 megakelvins and 1 gigakelvin, the rates, the triple alpha proceed to these two processes, no? The alpha plus alpha in beryllium 8 ground states, and then the beryllium 8 ground state plus alpha that produce carbon-12 in the oil resonance state, then decay. And this is a very well-known picture. Also yesterday it was recorded by Sandro, and so essentially the rate is dominated by these two resonances. Okay, so and this is the present state of the art from the experiment. Essentially, the rates cannot be directly, at least right now, measured. But however, since we can assume that the oil resonance dominates, we can derive the rates by measuring this parameter here, essentially. So the various gamma and the energy of the oil resonance. And this is true in this range of temperature. But outside this range, the situation is much more complicated. 5 minutes. Okay. So especially at high energy, we have these problems of higher state may be excited, and at low energy instead there is not enough thermal energy to make the process in 2 steps, no? And so some sort of 3-body reaction should be invoked in that case. And this is done by various theoretical approaches. And in particular, I have analyzed this one in 2015 by Sun et al. That used this very complicated solution of the Schrödinger equation, and they got these results. Okay, the RGB tip, the temperature at which the helium flash take place at the RGB tips is in this region here of temperature, and here there is a zoom of that, and you see this is the experimental results. Now the NACRE, their uncertainty, which is quite low, as you can see in this range of temperature, but this is the theoretical prediction. It is almost 50% larger. So what happened if I adopted the theoretical one rather than the observed one? And this is how the picture is modified. And you see that I got fainter RGB tips, and this will increase eventually our bounds. So this is the kind of thing that should be understood. I don't know if with experiments or improving the theory. So if I have 3 minutes, okay. So the other things that I wanted to show you is the questions of the parameters. We go ahead in the evolution, so we also consider helium-burning star, which are here. So the F parameter essentially is the ratio between the number of stars observed in the horizontal branch and the number of stars in the brightest part, no, above the ZAP, the 0H horizontal branch here. This is typically introduced by Igo Iben in the 60s, I think, to measure the helium content of star, because this parameter does not depends on the metallicity of the cluster, but depends on the helium content. So essentially, the number of stars is proportional to the evolutionary time scale. So actually, this ratio measures the ratio of the evolutionary time scales in the helium burning and in the upper part of the red giant branch. Okay. So this is what we have measured in 59 globular clusters as a function of the metallicity. And this is the average hair, the weighted average with the hair that we got. So, and this is the theoretical recipes we have developed in order to get the parameter. Essentially, we starting from the evolutionary tracks of horizontal branch and red giant branch stars, we got this synthetic diagram. This is not an observed diagram. This is theoretical. Okay, so we can essentially do exactly the same we have done for the observed clusters, and you get the theoretical NHP or NLRP. So there is probably most of you know that these problems of the multi-populations in the globular clusters, there are different populations, a first generation of stars that essentially share an helium content, which is almost the cosmological one, the ones that come from the BBN. And but there is a second population that is helium enhanced in most clusters, not in all clusters, but in most clusters. And so how this modify the parameter is shown here. In red, the helium enhanced population, in black, the normal helium populations. And you see that these affect the theoretical hair. So how to prevent this process? So helium enhanced stars are smaller in mass, and they populated these blue tails of the horizontal branch. You see, that is not present when the difference in helium is small. So the way is to we have not considered in our sample cluster that present these blue tails, these extremely blue tails, and this may safely prevent this kind of problems. Okay. So this is the results, the theoretical results. This is what we measure. And this is, once again, in this case, this is correct. This is the coupling between actions and photons. And you see that the presence of action, the production of actions accelerate the helium burning. So, and these produce a lower hair, no? A lower numerator of the ratio between number of HB star and number of red giant branch stars. Okay, so this is the theoretical receipt. So we have, of course, uncertainty also in this case on the measure of the hair, on the Y uncertainty in the theoretical recipes, in particular nuclear reaction. The most important are the rate of the CNO. All these stars have a CNO burning shell that produce most of the luminosity of the stars and contribute. Then once again, the triple alpha and the carbon-12 plus alpha reactions. And at present, this is the most important uncertainty. So how to evaluate the impact of that with the Monte Carlo techniques with 5 parameters, these 5. Okay. This is the effect of varying Y, the helium content within this error bar. And this is the effect of varying R within this error bar. And here you have the effect of varying on the theoretical air, varying the nuclear reaction rates within the error bar. And the most strong dependence is from the carbon-12 plus alpha, of course. And you know the problems of the two subthreshold resonances that may interfere. This is the latest air matrix calculations performed by the Bohr et al. In 2017, and the 30% error comes from this error bar here. But by the way, a destructive interference will move hair downward, and so give a lower strength of the interaction of action with photons, while a constructive interference goes in the opposite direction. So this is what, and this is the results that we got with in this framework right now. Of course, this may be improved by improving the reaction rates, in particular that of the carbon 12 alpha. And this is the slide that I have told you. This is the last one, Sandro, sorry. And this is the various experiments. I don't have time to explain you in details, but there are various experiments that are ongoing that try to detect actions. Essentially, this cast, baby Yaxo, and Yaxo. Baby Yaxo is under contraction at Hamburg at the DESI laboratory, and this is our project for the futures. And Cassie is at CERN, and what we can say about that? Okay, the yellow area at the constraint we get from the RGBT, this one, and from the HB, so the F parameter, this one. So we can say that these are the limits obtained by Lutz and Darwin, for instance, and we are well below. Okay, and we also cut part of what can be observed from this solar helioscope here. Is essentially this work. This is curious, Sandro. On top of this telescope, there is a big magnet. Okay. So an action produced in the core of the sun pass through this magnet. They are converted by the inverse Primakov into X-ray photons, and then below there is an X-ray telescope. Essentially, the mirror are here, and here there is the detector. So the end. So this follow the sun and try to detect actions in this way. Actually, photons. What measure is X-ray photons? Okay.
This is the future.
This is the future. Yes, this is the future. But what is important here is that with the stars, with astrophysics, we may reduce the parameter space in which the experimentalists should look in order to detect these particles. That's the idea. Okay, so that's all. That's the conclusion. Thanks.
Questions?
So worth pointing out, so you're talking about the triple alpha reaction rate.
Yeah.
So obviously that's dominated by the rate you came with, and there was the recent result of Kabidi where he saw a 34% higher rate, and it was in disagreement with the previous one. So there are further measurements that are going to be done on that, but there is the the outside possibility that the whole triple alpha reaction rate may be higher than originally thought.
Yeah.
So how does that if it were to have a 34% increase, how would that then affect your sensitivities?
Yeah, and of course this may have a great impact in solar evolution, not only for this kind of stuff, but in general for solar evolution, because helium burning is important in many astrophysical contexts.
Yeah, just to say, there is this increase of about 30% in gamma rad, but if you sum up, so gamma rad and gamma alpha, you have to get one anyway. So something is wrong, because if you now add these two numbers, so we are about one. So it has to be understood.
John, if I listen to Sandro's talks about the stellar evolution, I understand that all the 3D effects like mixing and matrix part is basically parameterized, because we have 1D models, and even for the solar model, the microturbulences are 3D effects. And so
how it impacts.
And you are an expert on that. So if you take luminosity of stars as the measure, and you account for all the uncertainties in our rate of modeling stars, can you really say that you need an extra effect from axions?
Yeah, that's the kind of the job that we are actually done. So to consider all the uncertainties, I had no time to explain everything. So, but in the slide that sorry. Okay, in the slide I have shown before, there is also a mention to these problems of the mixing. And this is particularly important for a burning star. We have to consider a different kind of mixing. The classical one that we use, that is semi-convections and so on, but also models with overshoot, with different amounts of overshoot and so on, in order to try to and there is for horizontal branch stuff, there is an additional problem that is some instability on the convective border that occurs near the end of the human burning that may prolong and so make the time scale longer. So you are perfectly right, but we have considered that in our analysis. But I had no time to explain everything, so I was concentrating on nuclear reaction. And for the red giant branch, in addition to nuclear reactions uncertainties, very important are the electron conductivity, as I explained, there is the neutrino rates, of course. So, for instance, the same small discrepancy between what we observe in the luminosity of the tip and what we predict may be explained by increasing the neutrino rates. For instance, by assuming a dipole moment, the magnetic dipole moments of the neutrinos larger than predicted by the standard models, and the screening, the electron screening is very important because we are in an intermediate regime screening. So in the old computations, people use weak screening, weak electron screenings for nuclear reactions, and these, of course, make lower the total reaction rates. So there are many. The equation of states, of course, also is important. Well, we have considered all these uncertainties. Yeah. And this is the reason for which we use Monte Carlo in order to analyze also the correlation between the various uncertainties that affect the models. So we have done this. It takes one RGB models require on a laptop 20 minutes, half an hour to be calculated up to the T. So very short times. But in order to populate the Monte Carlo, you have to calculate thousands of models. So these are required months for calculation. Aurora.
So a very naive question. So how do we consider these actions to be? So they should be massive. Maybe they can have a mass. They can have a charge. So they can also interact with the electron.
They are bosons. They are bosons.
They are bosons.
Yeah, they are non-Boole bosons produced by the breaking of this primordial symmetry. So they actually, what cosmologists say is that they can condensate in a Bose-Einstein gas after the productions, and this is the reason for which they could be have a colder matter, actually. So only no interaction with other particles, practically in practice, but we can see them also through the gravitational interaction that we see at the various scale, the dark matter, typical dark matter, cold dark matter, and so they have no charge, so the interaction is weak through this process that I have described, and they may have mass. The mass is an unknown, so that depends on when they were produced, and so the mass range is extremely large, from nano electron volts to 100 of keV.
Yeah, I got a bit confused because they were somehow feeling this magnetic field in the telescope somehow. So I was thinking they could have a charge.
Yeah, the idea is that the mass is small. The general idea that the mass, or at least for actions or halves, because halves also are interesting, because in this theory, like string theory, there are many of these action-like particles that can be in principle produced.
So there might be some connection, in nuclear reactions. The Hungarian group is found indeed this kind of strange behaviors in very late
Yeah.
in carbon 12
There
and
is a state
alpha.
in iron 57, if I remember,
Yeah,
that is supposed to be,
just in case, like,
yeah,
with plastic
yeah.
minus.
Excellent.
So there's
70.
17 and a medio, let's
Sì.
say, and very good.
Yeah, that's, and this should produce from the sun, looking at the sun, should produce a monochromatic line in the X-ray from the sun. And this one is one of the target of Yaxo, baby Yaxo, and these experiments that I have shown at the end. Is one possibility. In addition to the Primakov or Compton, that is a thermal production, so with a very well-defined spectra, there is also this nuclear origin, possible origin, that could produce this light. So, and this could be very interesting because when you look at to a specific energy, this is the signal that the process should be exactly what you are in mind. So it's very nice.
Other questions?
Just one thing. Can you go back to one of your last transparent?
Ma io Alessandro farla ripartire. Sorry, which one?
Maybe the 10 before the last, something like that.
Okay.
Okay, this one. No, before, sorry. Okay, so I cannot see it very well. The first one is what? Nitrogen 14?
This is the nitrogen 14 P gamma, and this
Okay.
is because, as I told you, there is a nitrogen burning shell outside that
Yeah.
contribute to the total luminosity of the stars.
No,
About 50.
maybe it's not a question for you, but for my colleague. Could you check this?
This has been measured. This has been measured at Luna, essentially, in 2005, 2006.
Well known as the correct energy.
Yeah, because the energy is the energy of RGB or HB hydrogen burning shell. The gamma peak is around 50 kb, 50, 60 kb, and the Luna experiments with the gas target arrived at around 70, so very close. So you need a small extrapolation of the astrophysical factor, but in a region far from the resonance at 256 kb. And so the extrapolation is apparently quite safe.
Yes.
And the error bar at 70 kb, the experimental error bar is of this order of magnitude, less than 10%, 7%. Actually, the solar fusion 2 give 7% uncertainty. So this is a little bit more conservative. Okay.
But you know, these are indirect methods.
No, direct method.
This is direct. Okay.
This is right.
But some of us do indirect methods. So because this is known, it could be cross-checked. I mean, this is sure. This is, I'm sure, right.
Okay.
But we could cross-check our breakup method.
Ah, okay. Okay.
But
Yes. Yes. Yeah. Sure.
But you should convince the experimenter to do this. Can it be done? A beam of oxygen 15?
Yeah.
Yeah.
Whether it can be done with a better uncertainty is not so clear.
No, but because this we know well, you could cross-check your indirect method.
Sure.
Or calibrate it.
Calibrate.
Well,
exactly.
if there is a screening, or depends on where you go.
That's
When you
just-
go to lower, but not. Yeah, the screen, the Coulomb barrier, you mean?
Scanning from the electrons, if you got very low energy, then I guess.
Yeah, but this energy,
What's the
the screening, 50 kb.
50K?
No, so it's not.
Yeah, but here one should do the full breakup of oxygen. Sorry?
I mean, the synthetic current using Coulomb breakup method will be larger than the thermal.
But in fact, this is what I'm saying. I'm saying that it could be a way to calibrate this indirect method.
Yeah, sure.
In this case, the true value is known.
And eventually you can apply that to other reactions. Yeah,
Exactly.
yeah, that's a good idea. Yeah.
Any other comment, question? I have a comment myself. By looking at that plot, why for these clusters, the variation of Y with the metallicity, it should be reduced a lot. The Y over the Z. The trend of the
Sure.
helium abundance with the metallicity should be reduced respect to the values.
Why should be a reason?
Because now it's, let's say it's 0.28, just to say a number.
Yeah, but
26, almost 26, the primordial, let's say. Or well, we should
Right,
have
consider that
an increase between 24 something from the Big Bang up to 25 something.
yeah,
in
there
the
is,
most
there is
stellar core.
this is a little bit more, if you see.
25.5, yes.
So 25 and 26.
So between
This is 1 sigma.
the clusters, the globular cluster, and today the increase in the helium abundance was lower than it was expected in the past.
Yeah.
Half, I would say half.
Yeah.
Because in the past, the globular cluster, when the helium abundance was 0.23, the classical value adopted in the models.
Yeah.
And Pager was the one who computed the Y over the Z.
No, but the standard
So-
solar models tell us that the helium content in the suns is lower than believed in the past.
Even worse, is even reduced. So the amount,
reduced.
the increase of helium
Yeah.
with the metallicity is much lower than it was thought in the past.
Yeah, absolutely. That's yeah.
Yeah, good.
So actually, this is a bona fide in the sense that 26 is actually quite high.
Well, there was
Globular
an
cluster.
initial increase
Yeah.
of 0.01,
Yeah.
which is not very
But
low.
but the upper bound is fixed by the higher helium contents because this makes shorter the
Yeah,
helium burning.
Yeah.
So actually it's the 26 rather than the 24 or 25 that's affect that. So but I think that this is
something
quite
to
confident.
think about.
Okay.
Okay, thanks, Oscar again.